Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Daniel bin Shamsul Azri, student ID 20214599588, and my supervisor is Dr. Monarita, and I'm going to talk about study of physical and mechanical properties of using sugarcane bagasse as a biofiller in rubber compounding product. For chapter 1 introduction, for the first one is background of study. For the statement, Malaysian rubber industry is the 7th largest global producer of natural rubber and 8th largest consumer. Focus on tire, industrial rubber product, and consumable like glove and shoes. For supporting studies 1, biomaterials such as sugarcane bagasse in natural rubber composite improve the rubber substance biodegradability. And for supporting studies 2, the potential benefits and limitation of using sugarcane bagasse as a biofiller in tire manufactured by conducting a comprehensive examination of this problem. The goal is to contribute to the development of more environmental friendly tire material as well as to aid in ongoing waste reduction and environmental activities. For problem statement, the carbon black limitation. Carbon black offer high tear strength, modulus and fatigue resistant in rubber but experience diminishing return beyond a peak amount. The effect of transition to sugarcane bagasse is second point. Focus on sugarcane fiber as a reinforcing filler for sustainable practice. Investigation into the chemical, physical and mechanical properties of sugarcane bagasse SBA. For significance of study, the advantage of using biosourced material as a filler in rubber industry. For objective of study, for the first one is the effect of replacing traditional filler material with bio-based filler on the mechanical properties of rubber compound. For second objective is the incorporation of biofiller in rubber compound affect the curing characteristic and processing behavior. And the last one is the environmental and sustainability benefit of using biofiller in rubber compound formulation compared to conventional filler. Chapter 2, Literature Review. Introduction of natural rubber. For the first point is natural rubber is a biopolymer made of cis-1,4 polyester known for great elasticity and damping. It comes from milky latex in various span, with the heavier Brazilian string being the main source. And the next one is natural rubber is used in tire, machinery part, glove, toys, shoe sole, elastic band, eraser and sport gear. And the next one is ideal for application needing abrasion resistance, elasticity and damping shock absorption. And the last point is natural rubber is a popular substitute for synthetic rubber due to the high oil cost, often blended for improved properties. For rubber compounding, first off, there's a growing commercial interest in rubber material that offer both improved processing and solvent resistance. Well, natural rubber has some limitations such as resistant to oxygen and ozone, along with high gas permeability. This challenge pushed scientists to modify natural rubber, making it more versatile and competitive with synthetic rubber. According to Pereira on her thesis, who introduced a new family of polymer to address solubility issues and provide excellent processing characteristics. The innovation brings forth material that not only become solubility challenge but also offer good processing characteristic. This means natural rubber can now find application in a broader range of industry, competing more effectively with synthetic counterpart. Moving to eco-friendly composite, natural material plays a crucial role in developing environmentally conscious product. The second point is natural material like sisal, hemp, jute, kenaf and etc. are commonly used for environmental friendly composite. Agricultural waste and byproducts are increasingly utilized for composite development, promoting a circular economy. According to Chang, BP, waste-derived material, when processed and purified, serve a versatile and eco-friendly filler for various polymer systems, including rubber. Shifting our focus to biocomposite. This material offer a sustainable solution to environmental challenge and limited petroleum resource. Sisal, hemp, jute and etc. are popular natural filler for environmental friendly composite. Agricultural waste and co-products are gaining attention for biocomposite, developing due to their low cost, abundance and satisfactory performance. Concluding our discussion, waste-derived bio-based filler holds significant potential for biocomposite derived from agroforestry and agricultural waste biomasses. This material, after processing and purification, can serve a multifunctional green biofillers for different pollen systems, including rubber. In the summary, the utilization of both natural and waste-derived material pave the way for more sustainable and eco-friendly solution in rubber compounding and biocomposite. Chapter 3, Methodology. This is the process. For the first one, I prepare master batch. I create a master batch using compound around 1.2 kg of rubber. The second one is I produce a homogeneous master batch sheet around 6 mm thickness. And the next procedure for formulation and division, I divide a 428 gram section of the master batch sheet into 4 equal pieces, added an appropriate filler to each section based on formulation base. And the third one is compound homogenization. I combine MBT with sulfur according to the formulation, homogenize the resulting compound to create 6 mm thick layer for the final stage. And as you can see, this is my content of material per 100. And this is my testing flowchart. Chapter 4, Result and Discussion. For cure characteristic testing, the table shows the result of 3 compound, pure gum, carbon black, and sugarcane bagasse H SPA. The test measure the curing time, TS2, minimum torque, maximum torque, and delta torque of each compound at temperature of 170 degrees Celsius. The result for pure gum can serve as a baseline or reference point for comparison with biofiller containing compound. The scorch time, cure time, Muni viscosity, and curing index are essential parameters that indicate the processing and curing characteristic of the rubber compound, while carbon black is a common reinforcing filler in rubber compound. The lower scorch time and higher cure time suggest change in processing behavior compared to pure gum. The increased Muni viscosity and maximum torque indicate enhanced reinforcement, while the lower cure rate index suggests a slower curing process. The result for SPA show a further reduction in scorch time and increase in cure time compared to carbon black. The higher Muni viscosity and maximum torque suggest potential reinforcement effect. However, the lower curing index indicate as a slower curing rate, which may impact processing efficiency. For hardness testing result, reveal distinct mechanical properties of rubber compound with various filler. Pure gum exhibit consistent hardness around 8.5, indicating stability without additional filler. Carbon black, a reinforcing filler, significantly increased hardness to around 46.0, enhancing mechanical strength. Sugarcane bagasse H SBA introduced variability in hardness, 54.17 to 58.5, suggesting its potential to reinforce the rubber matrix. While SBA show a promise as a biofiller, further optimization studies may provide insight into a consistent impact on hardness in rubber compounding application. Overall, the result underscore the diverse effect of filler on rubber compound mechanical properties, with SBA demonstrating potential as biofiller. For abrasion testing, as we can see, based on the result, pure gum consistently exhibit the highest volume loss across all set, indicating the highest susceptibility to abrasion among the tested material. For the carbon black, shows some variability in performance across set, making it challenging to determine the clear trend. And the last one is SBA, sugarcane bagasse H, demonstrating an increase in volume loss, suggesting a potential reduction in abrasion resistance. For density meter testing, in the realm of rubber compound filler, pure gum source from rubber tree latex stand out for its inherent suppleness and low heat accumulation, improving flexibility, resilience, rip strength, and abrasion resistance. Carbon black, a popular reinforcing filler, enhanced tensile strength, wear resistance, and durability due to its large surface area and excellent reinforcing qualities. However, its high density contribute to the overall compound density, as we can see in the result. And the last one is Sugarcane Bagasse, an environmentally friendly filler derived from agricultural waste, offer increased hardness and stiffness with a moderate density, striking a balance between reinforcement and sustainability. The optimal choice among these filler: pure gum for elasticity, carbon black for strength, and Sugarcane Bagasse for a sustainable solution. Depends on the specific requirement of the rubber product. Guide the selection for a harmonious blend of qualities tailored to the intended application. For the last testing is rebound resilient testing. The test results show that pure gum has the highest rebound resilience, followed by SBA and then carbon black. This means that pure gum is the most able to recover its shape after being deformed by an impact. SBA has a higher rebound resilience than carbon black, which suggests that it may be a viable replacement for carbon black in rubber. And that's all for the testing. I'm sorry to inform you that the tensile tester at lab, which is crucial for conducting tensile strength test, has unfortunately been out of service since week 11 due to technical issues. The machine encountered a malfunction and the technician has been actively working on resolving the issues. Despite their effort, it appears that the repair will take more time than initially anticipated. So, for the final conclusion for this thesis, the study investigated the potential of Sugarcane Bagasse SBA as a bio-based filler in natural rubber composite, aiming to improve sustainability and reduce reliance on traditional filler like carbon black. That's all from me. Thank you.